friends, in this video we are going to study about the digital frequency meter, which is also known as frequency counter. In this video we are going to study that what is the use of digital frequency meter and what is the construction, working and applications of this digital frequency meter. So let us start with our topic. The digital frequency meter, also known as frequency counter, it is a device which is used in the laboratories for the measurement of frequency in a circuit. So whenever we want to do the frequency measurements, we are going to use the digital frequency meter. This meter is going to give us the output in a digital form. So we are going to get the numerical values for the frequency of the circuit. So digital frequency meter, it is a device which measures and displays the frequency of any periodic waveform. It is essential that the waveform which is given as an input to the device, this frequency meter, it should be a periodic waveform. Then only we are going to measure the frequency of that signal. This digital frequency meter, it operates on the principle of gating the unknown input signal into the counter for a predetermined time. The input signal whose frequency we want to measure, we are going to gate that signal and then we are going to pass it into the counter for a predetermined time, so that for a particular period of time we are going to pass this signal through the counter, and this counter is going to count the number of pulses passed through it. Okay, and because time we already know, so easily we can calculate when we are measuring the number of pulses passing through the counter, so we can measure the frequency also. So that is the principle of this digital frequency meter. Now here we have used the term gating. So what this gating means? So this term gated, it comes from the fact that we are using an AND gate or an OR gate. Okay, so from this gate term, from this gate word, this gated term has come out. And this AND and OR logic gates, they are used for allowing the unknown input signal into the counter which is to be accumulated. Because what we are doing in the digital frequency meter, we are passing an unknown signal with the counter for a fixed time interval. So the number of pulses which have passed to this counter for that period of time will give us the frequency of the input signal. So this gated term, it is coming from this and the OR logic gates, that we are using these gates for allowing the signal to pass through the counter. Now let us come to the block diagram of this digital frequency meter. So this is the basic block diagram of a digital frequency meter. It is having various parts: counter, a gate, Schmitt trigger, attenuator, decoder and display unit, divider and clock oscillator. The clock oscillator, it is going to generate a clock pulse which is then divided and given to the gate as an input. So this gate will have one input as the clock pulse, which is having the same frequency as the input signal, and here we are having a Schmitt trigger and an attenuator. The input to the attenuator is the signal whose frequency we want to measure. Now this output of this gate will be given to the counter. Counter is going to pass this gate signal for a particular period of time. So for the number of pulses which has passed through this counter, counter is going to count that value and give it to the display unit, and this display unit will give us the output, that is the frequency of the signal. So this was the basic block diagram. Let us study the different parts of this block diagram in detail. So different components of the block diagram were a counter with its associated display and decoder circuitry, a clock oscillator, a divider and an AND gate. So the counter used in this frequency meter, it is a binary coded decimal counter which is going to convert the BCD output into a decimal output. So here in the block diagram you can see that here we are having the counter and the associated decoder and display unit. So counter, because it is a BCD counter, it is going to count the value in BCD. So this BCD value is converted into a decimal value by the decoder, and then it will be displayed on the display screen. Now here we are having a gate enabled signal. This gate enabled signal is of a known time period. We know the time period, or we can say we know the frequency of this gate enabled signal, and this signal is generated by a clock oscillator and a divider circuit. And these two circuits, they are going to provide this gate enabled signal as one end of the gate. Here we are having an AND gate. So one input will be this gate enabled signal whose frequency, or we can say time period, is known to us. So clock oscillator, it is going to generate the clock signal. It is we are having here a divider circuit, and the signal whose frequency is known to us or known time period signal will be given as one input to the AND gate. Now the counter is going to advance one count for each transition of the unknown signal, and at the end of the known time interval, the contents of the counter will be equal to the number of pulses of the unknown input signals that have occurred during the time interval t. Now each time the counter is going to advance by one value, it will start counting from 0. Each time it is going to increase by one value for each transition of the unknown signal. Like when the unknown signal, it is going to complete one cycle or one transition is completed, the counter is going to update by 1. So we can say that the contents of the counter, it will be equal to the number of the periods of the unknown input signal which have passed during the time interval t. So the number of pulses, and for a known period of time, like suppose for 1 second we have said that for 1 second this number of pulses have passed the counter, like 5 pulses have passed. So its frequency will be, time period is 1 second, so frequency will be 5. So in this way, the value which is displayed on the counter, it will be proportional to the frequency of the input signal. So directly we can read the frequency of the unknown signal by reading the value displayed on the LCD screen. Okay, so the contents of the counter, it will be proportional to the frequency of the unknown input signal. Let's take an example. Suppose that the gate signal, the gate enable signal, it is for 1 second. Okay, and the unknown input signal, it is of 600 hertz and it is a square wave. Okay, so for 1 second, this unknown signal whose frequency is first unknown to us, if it is passed through the counter, then it will be like for 1 second the counter is going to count up to 600 value. So for 1 second, how many pulses have passed through the counter, that will be equal to the frequency of the input signal. So input signal, its frequency is unknown to us. When we have passed this signal for 1 second through the counter is giving us an output of 600. So for 1 second, 600 pulses have passed, so its frequency will be 600 hertz. So this was the block diagram, and we can say the construction of the digital frequency meter. If we talk about its working, so let's try to understand the working of this digital frequency meter. For this, we will draw some waveforms. So these are the waveforms of the signals in the frequency meter. Here you can see that in the block diagram we have seen that to the attenuator and Schmitt trigger, the input signal whose frequency we want to measure is applied. Okay, so the first waveform is the waveform for the unknown input signal whose frequency we want to measure. Then we have the AND gate here. So there is an enable signal, the gate enable signal, and the second waveform for the gate enable signal is shown here. When this enable signal is active high, means its value is active, then the gate is going to be enabled, it is going to work, AND gate. Okay. Now to the counter, a clear or the reset pulse is applied. So the third waveform is for the clear pulse. Then the output of the counter. Okay, that what is the output and how we are going to measure the frequency through it. Now first of all, when a clear pulse is applied to the counter at time t equals to t naught. So at t equals to t naught, means before this t1 time, just a clear pulse is applied to the counter so that all the contents of the counter, they are cleared and the counter is set at the value of 000. Okay, all the contents will be cleared, it will be at 0 position so that the counting can start from 0. Now when this gate enable signal is high, okay, so this gate enable signal is high, means the AND gate is active, so whatever will be the input, that will be the output of the AND gate. Okay, so at T1 this gate enable signal is high, so this input signal is the output till the time T2 where this gate enable signal is up till that position where the gate signal is high. So this is T1, this is T2. So between this whole time when this gate enable signal is high, whatever is the input, that will be the output and the counter will start counting these pulses. So the number of pulses which have passed through the counter during this time period T or this time interval T2 minus T1, that will be the frequency of the unknown signal. So how this frequency meter work? First, a clear pulse is applied. Prior to T1, means just before the time T1, the gate enable signal. So just before T1, as the gate enable signal is low, so due to, because the gate is not enabled, so the output of the AND gate, it will be low. You can see here that just before T1 the output is low. But after T1, or we can say that between this time interval T2 minus T1, as this gate enable signal is going from low to high, so whatever is the output of the AND gate, it will be start counting, the counter will start counting. Okay, so the output of AND gate will changes according to the input. So between this time interval T1 to T2, because the gate enable signal is high, so the output of the AND gate will be according to the input signal. The unknown signal is going to pass through the AND gate, so output will vary according to the input and the counter, it will start counting. Now after T2, gate enable signal is again low. So the counter will stop counting. Okay, so the number of pulses which have passed through the AND gate during this time interval T1 to T2, the counter has counted those pulses. So the number of pulses or the number of counts shown on the counter, that will be equal to the frequency of the input signal. Because for a particular time period, suppose for 1 second, T1 minus T2 is 1 second. So for 1 second, the number of pulses which have passed, that is called the frequency. So if we make this time interval equal to 1 second, we can say that whatever the number is shown on the counter, that will be the frequency of the signal. Suppose whatever example I have taken earlier, that when for 1 second, if the number of pulses passed through the AND gate or the counter has shown 600, it means that the frequency of the signal is 600 hertz. Okay. So the counter has counted the number of pulses that have occurred during the time interval T. So the resulting contents of the counter, they are a direct measure of the frequency of the input signal. So we can directly read the frequency from the output, that is from the counter. So in this digital frequency meter, we are measuring the frequency of an unknown signal by using a counter. We are getting the direct reading from the contents of the counter. Digital reading we are getting, means we are getting the numeric value of the frequency. Okay. So I hope that this topic, digital frequency meter, is now clear to you. Thank you.